Hello, everybody. Chief Meteorologist Steve Templeton here. Steve's Storm School is in session, and this will be a live Q&A so that kids can learn about weather. So when your kids kind of type in the comments, why don't you type in your name and age. And you can type in your name and age even if you don't have a question. I'll try and give you some shout-outs. But name and age and a question, and we'll talk a little bit about weather here. We'll give it a second for more people to join. One of the things you'll see is I'll flip the screen to this. I have some really cool graphics that I'll flip through to help explain some of the weather concepts we have. Updrafts, downdrafts, that's going to be on the quiz, by the way, so make sure you memorize that. I have some videos, some really cool stuff here. So a lot of good stuff that I will get to eventually as we kind of build an audience a little bit. How's everybody doing? I hope you're hanging in there. Gavin, age 8, joining us. And Sean, who's 10, from Troy, Missouri. I really hope you guys are hanging in there and doing okay with the homeschooling. Know that mom and dad are doing their best. It'll be tough at times. It'll be boring at times. Hopefully you're getting out, moving and walking, running outside, playing basketball, taking a bike ride. Sienna, age 8. We have Will, who's age 8 as well. Do you mind if I leave the lights up? Because I'm going to probably walk over there and show them the green screen.
I'm turning them all on. We're planning on doing a 2 o'clock cut-in.
Okay.
I'm getting ready for that.
Okay. So we have about a half hour because they're going to do a cut-in at 2 o'clock. So why don't we get started? Let me know what your weather questions are. Actually, one of the things, let's see, Jack, who's age 8, he's excited to learn more about storms so they are less scary. I'm totally with you, Jack. In fact, a lot of meteorologists start off scared about weather. They learn about it, so they overcome that fear, and then all of a sudden they love it, and they become meteorologists. Don't worry, they're messing with the lights. No worries, Greg. They're messing with the lights a little bit as they prepare for a 2 o'clock cut-in here in the studio. We will learn about weather and storms, Jack, I promise. But one of the things I want to do is just kind of show you what's going on here, where I am. I'm in studio now, so I'm not in my house, but this is my little setup. We'll go through some of those cool graphics here in a second. Make graphics here. This is the studio, though. I mean, this is it. So you're kind of getting a behind-the-scenes look. I have no clue what that is. That's weird. Greg, do you know what those things are? The tubes?
That's the emergency cooling system for the terminal room over there. It's off the air conditioner up on the roof. So if the air conditioner in the terminal room would happen to fail, they would bring these tubes over through the hallway into
and cool
that
it down
to cool all of the core equipment.
So that's emergency cooling for a section of the station that has a lot of equipment going on that can overheat. When we do our newscasts and weathercasts, there's no camera people here, so the cameras are robotic. Greg, who you saw there, is one of the masters who knows how to program these, so he works to program it. And this is my view. This is what it looks like when I'm doing weather. Now, that camera right there would turn to me. And then if you look, there's a green screen, and you're like, well, where are your graphics? There are no graphics. So you can't see it right now, but when I'm on the air, my graphics and me would be there. It's like me watching myself on TV. So what you do is you look into the camera and you say, hey, everybody, let me tell you about the weather. And then you turn and you watch yourself on TV, and you would normally see yourself in maps, and you'd point to what you need to point at. You never look back this way. And so the reason we do that is because if I was doing actual weather, like I had maps here, first of all, I'm turning away from you. Plus, you would see my behind and my backside on TV. No one needs to see that. The camera adds 10 pounds. It's really nasty. You don't want to see that. So you don't turn your back to people when you talk to them. You talk to them like this, face to face, eye to eye. So this allows me to talk to you into the camera, eye to eye, but then I can point off to the side at what I need to point at, and then I turn back to you. But yeah, that's our studio. I thought I'd give you kind of behind the scenes look here. And then this is what it looks like from the anchor's perspective, looking back at our green screen. And you can make that green screen any color. You can make it blue, orange. We make it green because I don't have any suits that are that color, thankfully. It's kind of a, no offense to anyone who has that color green suit, but it's different, we'll say that. Avery, age 11, is from Afton, and Stella, who's age 8. Let's see. We also have Aiden Carr, who's from St. Louis, who wants a shout out. Luke, who's age 9. And go ahead and throw out some weather questions. Let me try to get things started, talking a little bit about what I think. Oh, That's actually interesting. I was going to talk about updrafts, and Bryn, who's age 8, wants to know how hail forms. It turns out it forms in the updraft. So I'm going to switch over here. And so there's really 2 important parts to a storm. Hopefully you can see that real well. There's the air going up, and that's the really important part for the hail. But what goes up must come down. And that's the part you feel, whether it be the splattering of the wind or the rain or the hail that's coming down. So that's hail coming down. But hail actually forms in this part up here. It actually bobs up and down, up and down. You know, the height of a thunderstorm is 1.5 to 2 times the height of Mount Everest. So if you can take water and thrust it up higher than Mount Everest, it's cold up there. That's why mountains, you see the brown, 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 and then it's white at the top. So it's really cold. So if you can take water and thrust it up really high, the water in the air that we can't see, we can't feel it, I can't touch it, trust me, there's moisture in the air. But if you could take it and throw it up to 1.5 times the height of Mount Everest, you can get it to freeze into a little pellet. Now, it needs something to freeze onto. Could be a mosquito that got caught in that updraft. Could be another piece of hail. But bottom line is it will eventually freeze. Now, it may melt on the way down, but if it can freeze big enough, what melts and shrinks is only a little bit, and it hits the ground as a piece of hail. So it's actually getting that water to go up into the sky. And I'll show you what that looks like in these updrafts. You'll see all sorts of cool stuff here. Let me get a good updraft. Here we go. So this is from Daryl Hersman on YouTube, and he caught it on a Skycam. Look how it's just exploding upwards. Look at that. Whew. So there's more air going up, 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 and then eventually the air kind of sinks a little bit, and then another updraft kind of fuels it and gets it higher and higher. Notice how it's spreading out, too. That's creating what we call an anvil cloud. That's on a real strong storm. But the air going up is thrusting water up really high, and it's freezing. And then it kind of tries to fall to earth, but let's say the updraft is strong, like 120 miles an hour. A little pea-sized piece of hail is not going to be able to fall through that 120 mile an hour updraft. So the little pea-sized piece of hail gets caught back up, gets thrown up, gets a little bigger. Maybe it's the size of a golf ball. And it gets pretty heavy, so it starts falling. But then that updraft, whoop, makes it doesn't make that sound. That's for effect. Whoop, makes it go up again, and it gets bigger. Maybe it's the size of a softball. And then eventually, it's so heavy, it starts to fall down to earth. Even the updraft can't lift it up. It's so heavy, and it melts a little bit as it comes down to earth, and then eventually hits as hail. Did you guys have hail yesterday? Last night. Not everybody got hit, but some got a little pea-sized hail. Some got a lot of it, especially in Belleville. All right, let's see here. Gavin, 9, and Leah, age 8, from St. Peter's. Gavin has a neat birthday, 8, 9, 10. Oh, that's pretty cool. August 9th, 2010. Nice. Let's see, the Bradford says, look like a mushroom cloud from a nuke. Yeah, those explosive thunderstorms, especially when they're isolated, meaning instead of a big gray sky so you really can't see them, it's just that like one storm, and maybe it's 80 miles away, but you can really see the definition and the structure in it. It's fascinating to watch those develop. We've got the Russums that are on. I'm 8, and my name is Madison. Hey to Madison there. Caitlin wants to know how lightning is formed. Caitlin, you've actually formed lightning. You may not know it. If you've ever, especially in the wintertime, this happens. You go to reach for something, and like maybe a metal doorknob, and all of a sudden you shock yourself. You've created a little mini bolt of lightning. And the way you did that, especially in the wintertime, because otherwise the charge that you develop on your body leaks through the moisture in the air when it's rather humid out. But in the wintertime when it's dry, that charge stays on your body. And the way you develop a charge is you got to rub. So in a thunderstorm, what's rubbing back and forth is pieces of hail and water, and they're going back and forth, and they're rubbing against each other, and they create a charge. At least that's what we think. There's a lot we don't know for sure about weather. That's how we think the charge is developed. The way you can develop a charge, if we wear socks on carpet and you kind of rub your feet, you can develop a charge on your body. And especially in the wintertime, if that charge builds up on you, and a lot of it builds up, and you go to reach for that doorknob, bzz, you can shock yourself a little bit. Doesn't hurt. It's not a big deal. It's a mini thing of lightning. But that's kind of how lightning develops. It's static electricity. And it's this buildup of this electric charge. And we think that buildup of the electric charge in the cloud happens from the rubbing. And I'm doing the updraft and the downdraft. There's just air molecules going back and forth, back and forth. I mean, when you watch this updraft, for instance, just look how the air is exploding up and down. So air is just constantly going up, and then some of it's coming down, up and down. And so we think that the water molecules, and the ice particles specifically, are helping to create that charge. Let me show you what it looks like when lightning actually develops, because there's something that you don't see that's happening. All right, here we go. This is slow-mo lightning, and that's not lightning. It's the beginning of lightning, but lightning needs to build a path. So these are called stepped leaders. They're stepping down to the ground. They happen so fast, you think that it's one stream, but what's really happening is they're shooting to the ground like maybe 50 yards and back, and then another 50 yards out and back, and then another 50 yards, but it happens so quickly. And these stepped leaders are leading the way to build a path to the ground, and that path is going to be what we think of as lightning, what we see as lightning. So what you don't know is happening, and this is a super slow-mo camera that captures over 7,000 images a second that allowed us to see this. It's usually faint and so fast the human eye doesn't see it, but what you don't realize is before that bolt of lightning, there's all these stepped leaders that are trying to build a path down to the ground. You do not want to be in the path, because if you're in the path, you're the channel. Lightning's going to go through you, flash over you, and down to the ground. So these step leaders are building, and that's what we see here. Now let me rewind it, and I'm going to play it, and I'm not going to pause it. Step leaders, step leaders, step leaders. Boom, there's your lightning. And actually the light you see is a cascade of light going up. So energy's flowing down that channel, but the light was a cascade of light going up. It's a complicated atmospheric process. There's still a lot we don't understand about lightning. But Mother Nature always gives us that clue when you need to head indoors, and that's thunder. Now, you don't hear thunder in this video that I played you. This is from Tom Warner, by the way. And that's because it's slow-mo. So it would sound like this. It's boring, right? It'd be a long boom because it's slow-mo. But trust me, there was thunder. If this was played in real time and he had the audio on, there's always thunder with lightning. So lightning creates thunder. So if you hear thunder, maybe you didn't see the lightning, it was behind you, it was way off in the distance, you weren't paying attention over there, but if you heard thunder, even if you didn't see the lightning, there was lightning. 100%, has to be. And think about a thunderstorm. Have you ever seen one storm just kind of come along and like, boop, one bolt, okay, I'm done, I'll go away? No, thunderstorms produce hundreds, if not sometimes thousands, sometimes tens of thousands of lightning strikes. So a storm's going to come around and produce 50, 100, 150 lightning strikes. If you hear one thunder, you know that's one bolt. Well, there could be 50 more to come, 99 more to come. You don't want to be out in that. So that thunder is the way to tell you, hey, just get inside. And with lightning, you don't have to run to the basement. It's not like a tornado. You just need to be under something. In fact, here's a good example. Busch Stadium, that's the visitors' bullpen. No one was hurt from this. But if you hear thunder and you're at Busch Stadium, by the way, the players were even on the field. If you're at Busch Stadium and you hear thunder, you have my permission to tell your parents, Mr. Templeton said you gotta buy me nachos. Or go get a hot dog. Long as it's in the concourse, underneath, right? Because if you're underneath and you're covered, you're gonna be fine. You're not gonna get hit by lightning. If you're outdoors, you have a chance. And some people think, well, it always hits the tallest objects, doesn't it? Take a closer look at that picture I showed you. Look at the foul pole. Look at the upper deck. Do you know how lucky these people are? It didn't hit the lights. It came down and hit the visitor's bullpen. Lightning does not always hit the tallest object. That is a myth. Is it more likely? Sure. Does it always? No. How about Stella, who's age 8? How many shelf clouds have you ever seen before? The fact that you're 8 and you know what a shelf cloud is awesome. Good for you, Stella. I have seen dozens and dozens. I've seen a lot of shelf clouds, partly because I have storm chased a little bit, And they're easier to see. They're bigger than a tornado, much more wide. But also because we have a Skycam network, so we see a lot of them on the BJC Skycam network. But for those who are wondering what Stella's talking about, this is a shelf cloud. And it's going to play rapidly. There it is right there. And then I'm going to replay it and slow it down and pause it, okay? So this is the shelf. And what's happening is warm air is coming into the storm, and cool air is coming out. And as they collide, the warm air gets lifted up because warm air is lighter. I'm going to replay that. Warm air is lighter. So the warm air gets lifted up. As the warm air, which has moisture in it, gets lifted up, the moisture condenses. And condenses is a word that means water goes from being a gas, where you can't see it, to being a liquid. And you can see it, a liquid cloud. So that's really what this cloud is made of. Let me go pause it. Trillions of liquid water droplets. They were flying in here, they hit the cool air, they got lifted up, and they turned into this cool shelf cloud. Now, what does this mean? Why do we care? Well, it turns out this is usually a sign that strong winds are coming. All the rain is coming back here. See how cool that looks? Storm chasers call that the whale's mouth because it looks like the underside of a whale's mouth. And what it really is just really turbulent air here. But air is rushing out this way, and that air that's rushing this way out of the rain can sometimes create straight line wind damage. So a shelf cloud, not always, sometimes the wind gusts are 30 miles an hour. No big deal, right? Sometimes they're 80. Big deal. So if you're seeing a shelf cloud and there's no severe thunderstorm warning, it's still best to get inside, stay away from windows. But if you're seeing a shelf cloud and there is a severe thunderstorm warning, there's probably near 60 mile an hour or greater winds on that. Great question. Bailey, who's age 12, wants to know, can you still get struck by lightning inside a house through a window if it's open? Yeah, you can. Lightning does weird things. It tries to follow the path of least resistance in the electrical charge or in the electrical field. And we can't see the electrical field. So a straight line right down to the ground isn't always the path of least resistance and the easiest way for lightning to get to the ground. So lightning kind of does this thing where it follows that breakdown in the electrical field and we can't see it. And so sometimes that breakdown takes it on a path like this and then that and then this, and then it gets near a window and who knows, it could go right into the window. Like I said in that picture where it didn't hit the foul pole, which is real high, it went all the way to the ground. Why did it do that? Not exactly sure, but that just happened to be the easiest path to break down that electric field and get to the ground. So yeah, you don't want to be like during a thunderstorm. I know it's kind of cool to sit near a window, open it up and look out. I would say keep the window closed and preferably, don't be near the window because typically when you have a thunderstorm, you sometimes, not always, but have strong wind gusts. And what if that wind gust was 50 miles an hour and there was a tree limb that came down out of the tree and hit your window? Well, then you're sitting there right in the window looking at it. You don't want that. Luke, age 9, how many inches of rain was the biggest storm? Great question. I don't know here in St. Louis what the most rain we've seen, like in one storm. I can tell you that from my experience, that first round of flooding from the Merrimack River was epic. We had a December, I believe it was, with 11 inches of rain. And I want to say of that 11, like maybe 7 of them came down over like a 3-day span, or maybe the whole 11 inches was 3-day span. There's a lot of rain, and that helped spark that first round of flooding on the Merrimack River. But I've also seen the leftovers of a hurricane reach us and produce flash flooding with 5 to 7 inches of rainfall. Let me show you what I'm talking about with flash flooding. So flash flooding is where you get too much rain in a short amount of time and areas that don't normally flood. A street's not a river, but all of a sudden it can look like this. This was 4 inches in 2 hours. Too much rain, too little time. It can't drain into the ground. It can't drain into the sewers. And so what does it do? It sits on the road and then it starts flowing to the lowest area. Water always wants to go to the lowest level, so it starts flowing downhill. And that's how you end up with flash flooding. Too much rain in too short of time. Now, if you took that 4 inches of rain and you spread it out over an entire day, that would not happen. That would not happen. Let's see here. Oh my, yes. Who was that? Said, oh my, Stacy Weiss Milliken. Oh, yeah. Let's see. My grandma told me, this is from Sean Russum. My grandma told me that there is one kind of lightning that doesn't have thunder. Is that true? Sort of. First of all, grandmas are always right, okay? Second of all, she is right because there's a type of lightning called heat lightning. But really what it is, it's just normal lightning that's far away. And it happens a lot of times in the summertime when you have an isolated storm. So that's one storm, maybe it's 50, 60 miles away. But it's the only storm. And the skies are blue around you. And you can see it from 50 to 60 miles away. So you see the lightning. But the sound of the thunder, as it travels, gets softer and softer and softer, and it never reaches your ear. So you don't hear the thunder from a storm that's 60 miles away. It's just regular lightning. You don't hear the thunder. But some people like to call that heat lightning. Heat because it happens more often in the summertime. I don't like that term because I don't want people to think it's a real different type of lightning, but it just means you're far enough away that you're safe. If you hear thunder, you're close enough to be struck by the next bolt of lightning. If you don't hear thunder, you're safe. And you can sit there and watch that storm. Let's see. Are men really more... This is a good question. I'm going to have to look this up from Maria Page. Are men really more likely to get struck by lightning? I don't know the answer to that. I want to say the answer is probably yes. Because, so I can tell you this, men are more likely to get hurt or die from flash flooding. I know that statistic is true. And lightning, possibly, not to diminish the fact that women work outdoors, a lot of women do, but I think statistically, if you took the groups, you'd probably find more men work outdoors, and then if you work outdoors, you're more likely to get struck by lightning. Possibly, that's the way my brain's thinking through the statistics there. That doesn't necessarily mean that women are smarter and safer and men aren't, but I think it's a matter of positioning. How vulnerable are you? But look, bottom line, both men and women are vulnerable if you're outside and you hear thunder. And the Russum said, okay, thanks, you're welcome. How about Jack, who's age 8? He wants to know, how can you tell if a tornado is an F1 or an F5? Brilliant question. So first of all, there's this scale that we measure tornadoes. You can't walk up to a tornado and measure it with an anemometer, which measures wind speed. So Jack, what we do is we measure the damage. So experts from the National Weather Service would go and look at something like this, and they would say, okay, well, this is total destruction, but that was a garage. And this, the house is still there, but part of the roof is off. Here's another one. Part of the roof is off, some of the roof is on, one wall is gone, but notice this interior wall, it's still there. And we would compare that to the scale. It's the EF scale. It's actually called the EF because it's enhanced, that's the E. The F is for Fujita, Ted Fujita, the guy who created the scale. And he determined that you can look at the damage a tornado creates and estimate the winds. So it's really a damage scale and it's estimated winds. By the way, there's a series coming up soon on public television called Mr. Tornado, all about Ted Fujita. I cannot wait. He studied and taught at the University of Chicago, that is. Brilliant guy, came up with more than just this F scale. So I can't wait for that series to come out. So the answer to Jack's question is, how do you know if it's an EF0, EF5? Based on the damage. And some damage is not too bad, and some damage is really bad, right? So like, for instance, let's compare this. This was an EF2, where part of the outside walls are gone, but not all of them. Part of the roof is gone, but not all of it. So that's the weakest damage, 5 is the strongest. Then we can compare that to this. This was EF3 damage, where all the walls are gone, all the upstairs is gone. Much different damage, right? More damage. And stronger winds create more damage. But here's the thing. What if there's like the strongest tornado there ever was on Earth, and it hits a wheat field in Kansas, and it never hits a house? Well, our EF scales based on damage. So if all it does is create what looks like EF1 damage in a wheat field, then it's an EF1. If there's no structure for it to show us how strong those winds are, That's it. So there's a real limitation on the scale. It has to hit a populated area or a structure to give us an idea of how strong those winds are. But that's because you can't just walk up to a tornado. The lower wrestlers said, thank you so much. We'll have to check out Mr. Tornado. Yeah, I'm kind of excited about that. And the other thing is, he was just, I don't know him. I don't know a lot about him, but from what I understand, I've heard Dr. Greg Forbes, who was the severe weather expert on the Weather Channel, talk about him. Greg Forbes studied under him. It sounds like he was just like a passionate guy and just loved learning and figuring things out, and just like, just one of those people that you're so glad was in our industry in meteorology. Just really passionate about it. All right. Let's see how we're doing on time. Pretty close. They're going to do a cut in here in the studio in about 5 minutes, by the way. Liam, age 10, the toilet was still there, and that's why my mom always tells me to hang on to the toilet. Let me go back. I think I know what he's talking about. Okay, Liam, you're right. The toilet's there. I don't want you to be there, though, because, first of all, I don't want you hanging on to a toilet while the wall is gone and all this debris is flying in. You don't want that. I would rather actually have, if you were here, and you shouldn't be here, I would actually want you ducking down in the bathtub with a pillow over your head. Now, first of all, there's a basement, okay? But even if there wasn't a basement, I would go through this door into that hallway, because that's an interior hallway. Maybe there's a closet in that hallway, an interior room where you have more than one wall between you and the outside. That way, when the first wall gets ripped off, you have another wall to protect you. And that's what you need. You need to protect yourself from stuff like this flying around. So when you think about tornado safety, indoors, lowest level, basement preferably. But even if you don't have a basement, lowest level, and then put as many walls between you and the outside. I like to think about it like medieval times, and you're building a castle, and there's invaders. Well, is one wall going to do it? No, let's build 2 walls, and let's build a moat around it. Don't worry about the moat when it comes to tornadoes. But I'm just saying, put as many walls between you and the invaders, and it turns out in a tornado, it's the debris flying around, the basketball you left in the yard, the dirt and the pebbles, and maybe pieces of roof from a nearby house that got hit. That is all debris, and they are missiles. And if you have 2 walls protecting you, you're going to be much safer than 1 wall. Even if there's a toilet in there that you can hang on to, I still want you in the interior part where you have more walls. All right, they're getting ready to do a cut-in in here. Hey, everybody, thank you so much for attending Steve's Storm School. You all pass. I hope you learned a lot. Maybe you laughed a little today, too. I really appreciate you joining me. Thank you, everybody.